Okay, thank you, Alberto. Yes, thank you very much. It's an honor to be the first speaker after the organizers, so I hope I do very well. So this is a joint work with several people who have contributed at different stages of this work. And primarily, so this is my PhD student, Bart Deleu, who has done all of it, let's say. Okay, so this is shadowing approach to data assimilation. All right, doesn't work. So this is the outline of the talk. So first, I will talk about what numerical shadowing is. Then I will explain shadowing-based data assimilation, and I will talk about fully observed perfect models, and by perfect models, I mean when there is no model error. And then I also talk about partially observed and also imperfect models, meaning that there is a model error. And I will also introduce an ensemble shadowing-based data assimilation, and again, I will talk about partially observed models with errors, and also if the error is actually structural, and I will explain what that is. So first, I would like to give just a notation. So there is nothing new that hasn't been said this morning, but this is just an introducing notation which will help me to describe what shadowing is. So I will define a continuous dynamical system as z dot f of z. So this is a nonlinear mapping. This is a PDE, let's say, right? And then I will call that this phi Tn is an associated flow. So then what it means, it will be a numerical approximation of a dynamical system, right? So we have PDE, and then we transform to the ODE. So we have un plus 1 is equal to this mapping phi Tn from the previous time un. And then this is a time index that goes from 0 to n minus 1. So this is a state of dynamical system. I call it U. So this is a discrete. So I will talk about discrete systems. And we also have partial, both in space and time, and noisy observations, and I denote it by Y, which is a linear, and I think this is very important that I consider only now linear mapping. So H is a matrix, and XK is a true solution of the true dynamical system. So we observe it partially. So H is typically a non-square matrix. And the index K is a time index that goes somewhere between 0 and minus 1. So it doesn't need to go all indices, but somewhere in between. And yeah, there is also noise. So typically, noise is coming from a normal distribution with 0 mean and some non-covariant matrix CO. So this is observation error. And so that is a true solution, right? So we have a propagation xn plus 1 is equal to phi Tn, the same phi. So this is for perfect model scenarios, so the same dynamical system. So then the initial conditions are uncertain, right? So this is just a notation. So what the shadowing-based data assimilation is based on is a shadowing lemma. And the shadowing lemma is for nonlinear systems. So first I would like to introduce a definition of a shadowing. So the U from n0 to capital N is called an epsilon pseudo-orbit of this dynamical system z dot f of z. If the difference between un plus 1 minus this mapping Tn at the un in some norm is less than epsilon. So it's not, if it would be 0, then it would be just an orbit. But it's not 0, then it's called epsilon pseudo-orbit, and pseudo-orbit because it's not a 0. Right? So that's why it's pseudo, and epsilon because this norm is bounded by epsilon. And there is a shadowing lemma which was proved in 1995 that, so let U and 0 to n be an epsilon pseudo-orbit of this dynamical system. then under some conditions, and I'm not going to tell what are the conditions, there exists this xn. So xn is on the true orbit. So there will be points on the true orbit such that the distance between pseudo-orbit un and the true orbit xn is less than some delta in the norm. So meaning that at least at some points we will reconstruct the true orbit close enough by some delta. So what the Shedden lemma does, that the Shedden lemma actually guarantees that there is a solution in a delta orbit of the true orbit. However, it doesn't necessarily tell us about the uniqueness of solution. So there might be several solutions, but they will all be in the delta area of this true solution xn. Moreover, there are rigorous bounds on the global error of numerical integrations that, so with respect to shading, that are proven, for example, in this 1987. And there are also other papers, and for example, the Eric van Vleck has been doing this, and he's one of our collaborators. So this is the shading lemma. This is nothing to do with data assimilation yet, but the idea is to find a pseudo-orbit such that it's in a delta region of the true orbit. So that's what we do to, that's what we use to construct a shadowing-based data assimilation. And I call it Newton-based, but it doesn't necessarily require to use a Newton method. It can be used any other methods. But the idea is the following. Let's say we define this capital function Gn, and n is a time index, right? So then we have a difference un minus 1 minus phi tn un. And the idea is to find the zeros of this function g. So if you find the zeros of the function g, then we will have a solution of the dynamical system, of the discrete dynamical system. And what we are going to do, we are going to use the Newton method because it's a second order, has a second order convergence. And at this point, we initialize it at full observations. So I will leave these restrictions later on, but at this moment, I say that we observe everything, which is, of course, is not the purpose of data assimilation. The purpose of a data assimilation is that we do not observe everything, and we want to reconstruct the things that we do not observe. But for now, I say we observe everything. So what we do, we initialize Newton method with the full observations. So if I define by this J an index of Newton iteration and I initialize at the zero iteration with full observations, then I can write down Newton iteration is this. The next Newton iteration is at the previous one plus this correction delta, and the correction is defined in this way. So what are these? So G of U is the difference, right, the residual, and the P is the Jacobian of G. So there are some of the things that I would like to mention, and C of U is the this is the observation error. So there are a few remarks that I would like to say is that first of all, we do not compute G of U, we do not compute actually the Jacobian, but what we do, we use an approximation, right? So it's the same as an ensemble Kalman filter in essence, meaning that we do the action of the Jacobian on a vector, right? And then we use basically Taylor expansion to do that. And another remark that I would like to say that the difference with respect to the variational data assimilation and the variational data assimilation, we're looking for initial conditions such that we constrain over some time interval, especially with four-dimensional variational data assimilation. So at the numerical shading refinement, what we do, we reconstruct the whole orbit over the whole time at once. So what that means that we can apply this method over longer times than typically is with variational data assimilation. However, we have to have these long matrices and operate with them, so this is computationally more demanding than 41. Okay, so what we looked at the Lorentz 96 model, and we observed the whole system. Right? So this is, and we took 40 variables. The observation is all, so we have a time, assimilation time in 0.25, and the assimilation window is length 1, and then we have 25 of such windows. So here I display an error with respect to the truth and infinite norm. So the black is for the observations average over time, and the blue curve is for the var, and the red curve is for shadowing. And what you can see is that the red curve is lower than the blue curve, and this is mainly because with the shadowing refinement we can have the assimilation windows longer than with the variational data assimilation, so then the error decreases. Of course, we were not the first ones who was attracted by the idea of using the shadowing property of dynamical systems. So this is, I see two people at the third row who has been doing this for a while. And so this is pseudo-orbit data simulation, or PDA. So this is also based on shadowing lemma. So how is the Newton-based method different from the PDA? So the difference is that in the shadowing or Newton-based shadowing data simulation, we look for zeros of g of n, and the PDA minimizes the cost function, which is the Gn transpose Gn. So this is the least squared, right? And what in the PDA is used is the gradient descent algorithm, again initialized either at full observation or so-called completed observations. I will talk about it later, what is completed observations mean. So if you look at the full observations and perfect models, so then both shadowing, I will call Newton-based shadowing as shadowing method. The shadowing method and PDA are equivalent. Why? Because the shadowing method also gives a minimum to norm solution correction to the residual. So for full observations and perfect model, they're equivalent. What is the difference? So in the shadowing method, we use Newton iterations. So then, because the Newton has the quadratic convergence rate, we have a better convergence rate than gradient descent algorithm. So then, on average, the shadowing method converges in less than 10 iterations, while PDA requires more iterations, but this is again due to the gradient descent. So what we saw in literature, it was reported 1,024 iterations. Another thing is that the difference in the gradient descent, that there is an algorithmic time that involved in the gradient descent, and has to be chosen in advance or tuned with respect to the skill. And in Newton, we have no algorithmic time. But otherwise, for a fully observed system and perfect models, they're equivalent. Okay. So now I would like to talk about partial observation, because that's the whole point of data simulation, to reconstruct the variables that we do not observe. So what we introduced complete observation. It has been also done for a PDA. So what does it mean, that these complete observations? I will call it this curly Y. And so this curly I consists of the existing observations and actually any type of initial guess for the variables that we do not observe. So it could be either an initial guess or it could be climatological averages. It's just a matter of choice. So then we also need to have a covariant matrix of so-called completed observations, and I'll call it curly CO. And then again, it will have on the places where we do have observations, and we'll have the covariance matrix of CO. So this is existing. And at the places where we do not have observation, we will fill in is long time average for unobserved variables. So we will just run for long time dynamical system, and we plug in the covariance matrix of those variables. So then that's the same. So we do the same kind of procedure. So we initialize at the completed observation. So this y, curly y, is observations and some initial guess. And then we use again this full, the Newton method to find the pseudo-orbit. So that's the same. So just, you know, this now we have these curly COs over there. So it's the same. So this is just to explain what the partial observations, how we use partial observations. And now I would like to talk about imperfect models. So these are the models I will consider models with additive noise. And for this, at least for the first experiments that we looked at, we say that actually the true dynamical system is stochastic. So typically it's the other way around. People consider that the true system is deterministic and the imperfect model is stochastic. We do it the other way around. And the main reason for that, because it was known, the Shedden lemma is known for deterministic system, but there is no Shedden lemma for stochastic systems. So that's the main reason.
The correct way of thinking about it is that the true one is stochastically perturbed. What happens in your computer is deterministic.
Okay.
That's a scheme that I showed.
Right. Okay, so we say that the state of the true dynamical system is stochastic. So we have this additive noise, this eta hat. And eta hat is the true noise. I call it eta hat is the true noise. And then we again have partial observations. So what we do know is that we know statistics of the model observation error, right? We know that the observation error drawn is from normal distribution with zero mean and non-observation error, so covariance. And we also assume that the model error is drawn from a zero mean and also known some model errors, covariance of model error. So then the state of this imperfect model is a deterministic, so we don't have this true noise. Okay, so what we do, we use Levenberg-Marquardt regularization to show shadow and data assimilation. And again, we are not the first ones to use this. So this is the at least two references in 2013 and 14. So this is in the inverse problems, and this is variational. Both of them use Levenberg-Marquardt regularization. So what we do is that we say that we again initialize at completed observations, right? So we have this curly y naught. But now, if you look at this, so the first one is again this delta correction. But now, if you look at the delta correction, there is this new term. So these two, they were already in the previous ones for the perfect model, but now we add this alpha j CM. So CM is the covariance matrix of the model error, and this alpha j is some algorithmic time. So now there are two things that have been taken into account. Is the first one is the stopping algorithm. So the stopping time. So what we do, we say that we stop at the iteration such that we do not move far away from the observations. So what we do, we initialize at the observations, and as we iterate, we will go further and further away from the observations. And in the end, if this CM would be 0, we will basically find a pseudo orbit of of imperfect model. And this is not what we are after. So what we would like to do is we would like to put a limit. If you're moving further away from the observations, then we stop. So that's basically the idea of the stopping criterion. So if we plot over iterations a norm, this norm where we observe, so we see that this norm starts to increase, and at the point when it crosses this bound, we stop. And this R we choose to close to 1, it could be 0.98 or 95. So what we do then, the second thing that we need to take care of is this algorithmic time. So the algorithmic time, what it does, it basically ensures that this delta correction is not big enough so that we do not jump far away from this observation. So what we need to have is that we need to have delta sufficiently large at the beginning so that we have a speed speed up the convergence, but at the end we have to have this delta small such that we do not miss this limit. So this is just, we show using this Hanke principle, but I will not give you the exact formula for that. So we choose this that algorithmic time adaptively. Okay, so the pseudo-orbit data simulation has also been done for perfect models, and the difference with our method is that, so it, as I mentioned before, it doesn't find the zeros of Gn, but rather minimize this cost function. It also initializes at completed observations, and the idea behind is also the same, is that we do not want to have the pseudo-orbit of erroneous model, but we would like to stop before that. So that typically is a predefined number of iterations, and what this predefined number of iterations is tuned with respect to maximize the skill. So that's, in the essence, is the same as what we do, but we use the, not the skill, but we use the distance to the observations. And another point is that algorithmic time in the gradient descent has to be chosen in advance while we do it adaptively. Okay. So this is something I must say rather disappointing to me, because we have done, okay, so one of the things I wanted to put this morning in a slide for the Lorentz 96 model, but my keynote presentation crashed due to the highly, really big size picture. So I was lucky that I already had the PDF preserved before that. But anyway, so what I wanted to show on that slide, an experiment for Lorentz 96 model. So if you do for the Lorentz 96 model, and we observe every fifth coordinate, so what we could see that if you do the observations of a very, very long time, then the PDA and the shadowing-based experiments are equivalent. However, the variational data simulation performs poorer, and this is what has been already reported in one of the papers on the PDA, that because we have longer simulation windows, the shadowing-based approaches beat variational data simulation. But so if you look now at the Lorentz 63 model, and I haven't seen any publication PDA for the Lorentz 63, but so what we observe is that if we have observation of only x coordinate, so we do not observe y and z. And for y and z, we just use any initial guess. So we just run Lorentz 63 model and just pick any initial guess. So we observe every 0.05 time units, and we have a length of 10. And so if you look at the left picture, so this is the root mean square error of the estimate with respect to the true in observed components. So if you see all of these shadowing in the PDA and 40Y, they perform equivalently. So if you look at the right, on the right-hand side, and the picture on the right-hand side, and this is unobserved variable, so y and z. So what we observed is that the PDA performs much worse than the shadowing in the 40Y. And we must say we don't know why it's that, because we tried to look at the different time steps and number of iterations and etc., but we are not able to get the error lower. So maybe something you can tell me afterwards. But what we can see that the PDA or the shadowing in variational data simulation on the short time windows, they perform equivalently, but once you increase the simulation windows, then the shadowing outperforms the 40Y. I think I'm running over time. But anyway.
I can tell you now, it's because of the onion skin structure of the attractor. There's a certain paper on which the lead author is Bob Miller, 1994, where that was shown for the variational method.
Okay. All right. Thank you. Yes. All right.
It's the surface of the moon.
All right. Okay, so we also did it for ensemble shadowing data simulation. I think I have to hurry. So this is something else that we tried. We tried a structural error. So we used this paper of Malteni and others from 1993, where Lorentz 63 atmospheric model is coupled with a linear advection for the ocean model. So this is on the left-hand side. So we say this is a true model, so there is a coupling involved. And we say that our erroneous model is only the ocean model, but we observe the full system. So if you see, we have these eta terms, right? So they're just random noise. However, in the true system, there is coupling involved. So this is what we say, so, right? So then we observe 4 and 5, and what we would like to say is that we would like to reconstruct the component of atmosphere. So this is the figure that we show. So this is we compare it with randomized maximum likelihood. So this is an ensemble-based data simulation. And we show the mean squared error for ensemble shading method and RML on the top. So if you can see that the black curve is the error in the observation average over time. And what we observe is the shading is outperforming the RML this is in observed state, but also for unobserved state. This is on the bottom right hand. So this is unobserved state. You see the blue is the shading and the red is the RML. So this is high RML. I think it's 6 for E shading and 8 for RML on average. And this is just to show how the E shading is doing with respect to ensemble. So the black one is the truth, and then we have the blue curve is the mean, and then red plus minus 1 standard deviation. All right. I think So okay. So we also looked at the analysis of the shading methods. And so we looked at the well-posedness. So what we could see, we saw that the system is well-posed if you have fully observed, but if it's not fully observed, that it really depends on the Jacobian. So what that means, if you have over some time that the system changes a lot, then basically most probably the shadowing would fail. So that means that the simulation window has to be decreased. So then the open equations are still the accuracy given partial observations. So what we also observed that for linear system, the E-shadowing is consistent with respect to the first model, but inconsistent with respect to the second moment for ensemble Kalman filter. So it underestimates the variance, at least for linear systems. For nonlinear, it becomes complicated to analyze that, but we are working on that. And so in ensemble shading method, we looked at the Gaussian errors, or at least approximate the Gaussian posterior. So what we would like to do is look at the other posterior samples. Thank you.
Too many questions for the short time we have, but I'm going to take as many as possible.
Hello, thanks for the talk. I have just a comment on the shadowing lemma. So a key core property of the system to make this really effective is whether it's hyperbolic or not. So something I wanted to underline is that if the system is highly non-hyperbolic, as an example, it has variability in the number of unstable dimensions, that's something we studied recently, then this is at risk of failing somehow because of huge loss of structural stability.
Yes.
Just some comment, I think.
Yes,
I
thank
think
you very much.
You refer to the end somehow.
Yeah. That's certainly true, yes.
Okay.
Take one from Remy, take as many as possible, and we run.
Thanks for a very nice talk. I guess I have one observation and one question. The observation is when we do partial observations, when we first doing partial observations, we started with Lorentz 96, the two different perfect model with 64 dimensions. and then 32, and then 16, and then 8. Did it work with 4? Basically, we found with the perfect model and fairly much longer time steps than 0.05, we still tended to get it. It still tends to converge. There's a huge amount of information in the dynamics, as long as you have a perfect model. So then my second question is it's the issue of when you have real model inadequacy. It's not that you've tweaked the equations just a little bit. I mean, that counts, but very often you get things which you don't meet the shadowing lemma conditions.
Yeah.
More relevant is when you're dealing with the real world, you have things like Michael noticed, like there's things outside our light cone that we can't know. We definitely have the fundamental thing is stochastic, and there may not even be equations. It's a religious question, right? So do you think the shadowing lemma, do you think it's the same kind of shadowing when you're looking at the planet as it is when you're looking at two well-defined sets of mathematical equations, or do you think there's something sort of fundamentally different?
I think there is something fundamentally different. I mean, I would certainly hope that it's the same, but I think it's it's too optimistic for that. So I think there is really a fundamental difference between those those equations, as you say.
Any good ideas how to take care of them?
Well, improving the models, right? That's the, I mean.
There was one.
Oh yeah, just that there's I think a much simpler example to what Valerio was saying. If you apply this to the Henon system, then so if you apply this to an Anosov system and you have a very long time series, then the orbit becomes unique, right? There's only one shadowing orbit if you have infinite amount of time, but it's not the case if you have something like the Henon system where you have tangencies. Then you can apply this algorithm and you can see that you get two orbits that remain very close to one another.
But I think there is even problem of because when to find a pseudo orbit, you still need to have a numerical algorithm to do that.
Absolutely. Yeah,
That's it.
It's just a remark.
Yeah. So even already there, right? Because you have a numerical algorithm to solve it, so you will have a numerical error due to that.
Yeah. No, but I think so. I mean, we applied this a long time ago to a system like basically the algorithm you described, and you see you do get a non-unique solution. You can get one or the other orbit.
Yeah, sure.
Just a remark.
Yeah.
Thanks again, Svetlana.